Hello students, welcome to IMS GATE Academy. I started electronic devices and circuits in foundation course. In the last session, I did PN junction diode. But how the structure of the PN junction diode and what are the formulas will be employed in the PN junction diode. In today's session, I am going to discuss about the PN junction diode when it is forward biased, what is going to happen. When diode is connected in the reverse bias, how the functioning will be done, that we are going to discuss in this session. I will start now. Suppose I have taken the diode like this. That means the working principle of the diode depends upon the biasing of the PN junction diode only now. Two types of the biasings are generally used in PN junction diode. One is said to be forward biasing, second one is nothing but the reverse biasing only now. That's why we can write one point here now. The diode working principle depends upon biasing of the circuit. That is very important. Biasing depends upon the biasing only now. How many types of biasings are used in practical application? Two types of the biasing you know very well. One is said to be forward biasing, second one is said to be reverse biasing. So one is forward biasing. The second one is said to be reverse biasing. These are the two types of the biasings are generally used to make the PN junction diode on only. But I would like to explain what is that forward biasing. We can do now. I selected forward biasing. But in the forward biasing, just I will draw the diagram and I will connect the battery and what is going to happen, how the phenomenon is going to take place. I will explain now. I selected this PN junction diode. This is PN junction diode. There is a depletion layer. Depletion layer is existing here. This is P-type material. This is N-type material. Otherwise, even you are putting inside, it is not a mistake. You can put outside inside this P and N directly. This is P-type material. It is N-type material. I said already, because of the diffusion, certain number of holes move from P-type to N-type. And they becomes ions, you know very well. In the same way, electrons from the N-type enters into the P region. Then thereby their recombination of electrons and holes are taken place here. Recombination of electrons and holes. I said already, this is nothing but the depletion layer. This portion I said already, depletion layer or space charge region or high resistance region or built-in region. Any one of the name you can give. Depletion region, I can say. What I did here, I connected with a supply. I connected battery. Some voltage I connected only here now. How that battery is connected here? P-type material is connected to positive electrode of the battery and N-type material is connected to negative electrode of the battery. In this way, if you are connecting the supply to the PN junction diode, we say it is a forward biasing circuit. In this biasing circuit, what is going to happen? You please watch. P-type material contains number of holes. Holes are positively charged particles. N-type material contains number of electrons. They are negatively charged particles. This is negative electrode. Electrons are negative. Negative, negative, what happened? This side negative and negative you got now. This side positive and positive you got now. Because of the same polarity here, what is going to happen? Some force is created. That force can make the what now? These holes to make a move from P-type to N-type material. In the same way, the repulsive force which is created in between the what now? Negative electrode and N-type material will allow to develop the force. That force will allow to move the electrons from N-type to P-type. So holes will try to move from P-type to N-type. And electrons will move from N-type to P-type only, you can say. This is the phenomenon is going to take place because of the what now? Diffusion only now. But due to the what now? Because of the what now? Collection of the supply depletion layer is slowly it is going to reduce when diode is a forward biased. Whenever the depletion region is decreasing, what is going to happen? Electric field intensity in the depletion layer will be reducing due to decrease of the width only now. When the electric field intensity is reducing, minority carriers which are going to move from the N-type to P and P-type to N will be reduced. Because the electric field intensity, whenever it is reduced, drift current also reducing only now. That means the reverse saturation current, the drift current is, but here the reverse saturation current is going to decrease, we can say. The reverse saturation current is denoted by the symbol I naught. This side from P to N, it is going to flow the current due to the majority carriers, I can say. The current which passes from the N-type to P-type due to the minority carriers is said to be what? Reverse saturation current. The summation of these two currents, what now? We can get the total net current is available. That current is nothing but the diode current, we can say. So how that diode current equation can be taken here now? Now we can write when the diode is forward bias here now, the diode current is written like this only now. The diode current equation is the diode current, because you can expect the questions from this equation. The diode current equation is ID equal to, ID means diode current only now. ID equal to I naught into e power V naught by, V naught means what? But the voltage is going to develop here now, built-in voltage. That is nothing but the V naught or V, we can say. The V naught by eta into Vt. Eta into Vt minus 1. This formula is generally applied to find out the diode current when it is forward bias only now. Vt means we know very well, thermal equivalent of voltage. At room temperature, we know very well, Vt equal to how much? 26 millivolts. In the last class, I have done the what now problems also by using that value only. There, eta is called as a ideality factor. A name given to eta is nothing but ideality factor. Ideality factor, we can say. Its value will be taken as a what now? Eta equal to 1 for germanium. It is a fixed value. 1 for germanium, I can write 1 for germanium, 1 for germanium, and 2 for silicon. But you will not give in the, sometimes you will give in the problem, sometimes you will not be given this value only now. If not given, you can take these values. Yes, this is for silicon. 1 for germanium, 2 for silicon will be taken now. I said already thermal equivalent of voltage. Vt value is nothing but, how much I said? 26 millivolts at room temperature. At room temperature is possible, that value. At room temperature. Sometimes in the problems you will give 25 millivolts. 25 given means 25 you put. Not given means you can put 26 also. It won't be affected only now. Understand now. The information is more important now. When diode is forward bias, this work is more important. But when diode is reverse bias, how we can explain this? I will explain how you play was. Reverse biasing. Reverse biasing of PN junction. Reverse biasing of PN junction. Reverse biasing means what they will do? I selected here PN junction diode. I selected PN junction diode. There is depletion layer here. This is the depletion layer. In the depletion layer, we know very well, this is a P-type material, you know, this is N-type. This side you can have the holes, will move from P-type to N-type, and they can create their what now? Positive ions. Here negative ions are possible this side. Like that possible. Here we need to connect a battery in this form. In this way we can connect. The voltage source is to be connected. In the case of reverse biasing, the battery source is to be connected to the PN junction diode like this one. Here, P-type material is connected to the negative electrode of the battery. N-type material is connected to the what now? Positive electrode of the battery. In that case, we can say the diode is reverse bias. If the diode is reverse bias, what mechanism is possible here? What is going to happen? This is a positive, this is a negative, This is a negative, this is a positive. Because of the negative charges will be attracted by this side. They will be attracted by this side. Negative charges will be attracted by the positive electrode. Positive charges will be attracted by the what? Negative electrode. Whenever these are the negative and positive are attracted, depletion layer is going to increase. When diode is a reverse bias, what is going to happen now? The electrons and holes will not move towards the direction this side only possible now. That means P to N side, we cannot find any flow of charge carriers. In the same way, no flow of majority carriers from N-type to P-type. So finally, what we can say, the current due to the majority carriers equal to how much if I ask in the reverse biasing, you can say directly 0 current only it will flow due to majority carriers. But because of reverse biasing, some current will flow. That means when the depletion layer is going to increase, built-in potential is going to increase, electric field intensity is going to increase, then you can find minority carriers to flow from N to P and P to N. In that case, some reverse saturation current is going to flow in the reverse biasing circuit. Finally, what conclusion we can make in this particular circuit? When it is connected in the reverse biasing, the current due to the majority carriers is always 0. But some current is going to flow. That is a negligible amount of the current only now. That current we are going to call it as a reverse saturation current. When it is in reverse bias, we can say it now. Those points are very important in the reverse biasing now. Now we can do the problems based upon, one problem I will do based upon the what not diode current equation now. You can understand it clearly. A diode operates, the question is given like this. A diode operates at 300 Kelvin. At 300 Kelvin. At forward voltage drop. At forward voltage drop. Forward voltage drop. At forward voltage drop is given of 0.4 volts. Of 0.4 volts it is given in the problem. And carries a current of, and carries a current of, a current of 10 milliamperes. 10 milliamperes it is given in the problem. If voltage drop if voltage drop, is changed, voltage drop is changed, if voltage drop is changed to 0.42 volts, 0.42 volts, then value of current becomes twice, current becomes twice only now. The current is becoming twice. What are the values of? What are the values of I naught and eta? I naught and eta, it is given in the problem. This is one of the question from the diode. This is the given problem. How we have to do this question? You check it. What is given? You please watch. A diode operates at 300 Kelvin at forward voltage drop. 300 Kelvin is given, means room temperature it is. When it is maintained room temperature, means we know very well one value. Thermal equivalent of the voltage is nothing but the 26 millivolts. Based upon that temperature, we can say. At forward voltage drop is given, means diode is under forward biasing only here now. That means the voltage across the what now, diode is connected here now. Voltage drop across what? This PN junction diode is given. How much? 0.4 volts it is given. And carries a current of 10 milliamperes. When the drop of 0.4 voltage is taken place, the current which is passing through the diode, that means the diode current is given in the problem 10 milliamperes only here now. And also what is given? If voltage drop is changed to 0.42 voltage, that means the voltage across the PN junction diode is changing here now. Initially, it is at the voltage of 0.4 voltage. When it is changed to the 0.42 voltage, the current also changes, he says. That change of current is nothing but the twice. Twice means what is the meaning? Diode current in the first case is nothing but the 10 milliamperes. The diode current in the second case is nothing but the 20 milliamperes. It is possible. He is asking to find the values of I naught and eta value. I naught is nothing but the reverse saturation current, and eta is nothing but the ideality factor. These two values are required. Tirumala Reddy, good evening, sir. And here we can do this question now. What way we can do here now? But in a problem, it is given reverse. Sorry, in this problem, what is given here now? We can check now. The values of I naught and beta values are required. And I want to take in a problem. Initially, what is given in the problem? It operates at forward voltage is given 0.4 voltage. I say the forward voltage is given VF or VF also, V naught or VF, we can take it now, no problem. Okay, we can put V naught for example. Already we have taken now. Alright, directly I will use here now. Diode is given forward bias in the problem. When diode is a forward bias, means we know very well. Diode current equation is clearly known to you. What is diode current equation is given already? Diode current equal to, I gave the formula. Solution I am taking here now. Diode current equal to I naught into what I gave it, e power V naught by eta into Vt minus 1 I gave already. Because here the diode is forward biased. That is why I wish to select the what now? Diode current equation, as it is a forward bias. But the point what you have to remember is, whenever here diode is a forward bias, the depletion layer is going to be reduced. That is going to be reduced only now. That means the width of the depletion layer is going to reduce. At the time, electric field intensity will also be decreased. When electric field intensity is decreasing, the reverse saturation current also what happens? It is going to decrease only now. That means ID equal to I naught into something minus I naught is possible, minus I naught. This I naught value is a very, very small when it is forward bias. At the time, this current I naught into e power V naught by eta into Vt is a very large value only now. In that case, this I naught value we can reduce, we can remove, we can neglect also. It is not a problem only now. What I wish to say, this diode current is approximately equal to, we can write I naught into e power V naught by eta into Vt I will put. Minus I naught I want to neglect. Why sir? Just now I explained. Due to reduction of the what now? Barrier, due to the forward biasing, that I naught is very small, I neglected only now. I want to substitute this ID initially I have taken. What ID is given? Initial value of ID, what is given in the problem? You check it once. They are given voltage drop is nothing but the 0.4. Diode current is nothing but the 10 milliamperes is given. I will take diode current is nothing but 10 milliamperes. This is 10 milliamperes. Approximately equal to what I gave it? I naught. We need to find I naught. I naught into e power V naught. E power V naught means when diode is forward bias, drop across the diode is given in the problem. What is given in the problem? That is given as a 0.4 volts. Yes, we can put 0.4 volts, this voltage. V naught is nothing but 0.4 voltage, I can put directly. 0.4 volts. Divide by eta value required. Vt, thermal equivalent of the voltage, I said already, at room temperature at 300 Kelvin, at T equal to 300 Kelvin, we can say Vt equal to, I gave already 26 millivolts only. Fixed value at room temperature. That value I can put 26 into 10 power minus 3, I can write. That much value possible. This I want to take it as equation number 1. I want to take this as an equation number 1. But in the problem it is given when diode current becomes, when the voltage across the barrier is changed, diode current is twice is given in the problem. You check it here now. In the problem what is given? Voltage drop is changed to 0.42 voltage. The current becomes twice. Twice means 20 milliamperes I can put now. This diode current, second equation I can form 20 into 10 power minus 3. I naught is same. It will not be changed because the diode is the same. Understand now. And e power V naught voltage across the barrier is given in the problem. What is given? 0.42 voltage. I can put 0.42 voltage. This must be divided by eta into 26 milli. Vt is same. I wish to take this as an equation number 2. Like that I want to know down. But I want to divide equation 1. Equation 1 by 2 I want to take. Equation 1 by 2 I have taken here now for example. Equation 1 by equation 2 I want to take. Equation 1 by 2 means 10 power minus 3, 10 power minus 3 cancel. 10 by 20 is nothing but 1 by 2 I can get here. And this side I naught cancel because my aim is to find I naught and also eta value now. Here I naught and I naught cancel, this by this possible. E power 0.4 eta into 26 into 10 power minus 3 I can write. Divide by what I can put? This value. E power 0.42 by eta into 26 into 10 power minus 3 I can put. Minus 3 I can write. Here, this is e power something means I can take this to numerator now. If I have taken to numerator, 1 by 2 is nothing but the 0.5. This side e power, the denominator is same 26, this is also 26 milli, eta into 26 into 10 power minus 3, I can write directly. And in the numerator, what I can get? 0.4 minus 0.42 minus 0.02 I can get here now. Minus 0.02 by something is possible. Minus 0.02 by something is possible. Understand? This much 0.4 by minus 0.42 we can take it now. And E can be taken this side. We can take E to this side. Log ln of 0.5, ln of 0.5, that equal to how much? And I will get minus 0.02 minus 0.02 divide by how much? 0.02 by what I can get? Eta into 26 into 10 power minus 3. Eta into 26 into 10 power minus 3 is possible. Now, directly you can use the calculator, you can get something value. Eta equal to what I can get? Minus 0.02 by 26 into 10 power minus 6, minus 3, sorry, this is a minus 3, because milli only we got. This is 10 power minus 3 we are getting. And finally, 10 power minus 3 we can get now. If you are using the calculator, it comes as, this value will be 1.11 is possible. 1.11 value possible. That is the eta value. We got eta value from this, understand? And also I wish to find what value? I naught value. I naught value I can get from what? Equation 1 or equation 2. I am taking the what now? Equation 1. 10 into 10 power minus 3. 10 into 10 power minus 3, that equal to what is given? I naught. I want to find I naught value. I naught into e power, how much is given? E power, how much it is given here? We can note down e power 0.42 by E.042, 0.4 divided by 0.4 divided by eta into Vt. Eta is nothing but we got already 1.11 into Vt is nothing but the 26 milli. Use calculator, you are going to get the I naught value directly only now. That I naught will come as, you will get I naught value as 9.45 nanoamperes. 9.45 nanoamperes mostly possible. This current is always very small because reverse saturation current is mostly measured in nanoamperes only now. We are getting in nanoamperes. Understand? In this way we can tackle the problem. Just one problem is just enough. By using the what now? This formula you can do any sort of questions only. Next one I want to give in your hand. The next formula is now variation of I naught. I want to give variation of I naught. Variation of I naught. Variation of I naught I want with respect to temperature. With respect to temperature. With respect to temperature. With respect to temperature. This is very important. Sometimes you can expect the questions only now. That means a reverse saturation current will be increased by means of changing the temperature also here now. That means when the temperature is increasing more and more, I naught also increases more and more. Why it is increased, sir? It is a very simple. The increase of temperature is going to break the covalent bonds. When the covalent bonds are broken down, electrons are going to generate only now. Electrons and holes will be generating. The moment of the charge carriers can make the what now? Reverse saturation current to increase only, we can say. That is why anyhow variation of I naught with respect to the temperature means one empirical formula is there now. Empirical means here it is not derived, direct formula only now. There is an empirical formula for it is I naught reverse saturation current at T2. When the temperature is initially T1 and it is changed to the what now temperature T2, the change of I naught is possible. The change of I naught is nothing but I naught of T2 we can write now. That is calculated by the formula I naught into T1, I naught into T1 into 2 power T2 minus T1 by 10 by means of using this formula only. It is determine reverse saturation current at T2 only now. I will give one problem, then you can understand how this formula will be used in PSUs, even engineering services, even in the GATE exam, you will know only now. Just one problem I will give. If, question I will give, if yes, I will give the question now. If value of I naught, if value of I naught equal to 2 microamperes, 2 microamperes it is given. The current I naught equal to 2 microamperes at 10 degrees centigrade, at 10 degrees centigrade. What is the value of I naught? What is the value of I naught? What is the value of I naught? What is the value of I naught is asking at 90 degrees centigrade. At 90 degrees centigrade it is required. That is the given problem. I gave you formula. By using that formula, easily you can determine the reverse saturation current, how much it comes at a temperature of T2 only. How we can do this? I will do this problem. Please watch it. But in the problem, what is given? If the value of I naught, that means I naught is given 2 microamperes at temperature 10 degrees centigrade. What is the value of I naught at 90 degrees centigrade only now? T1 and T2 you can maintain in centigrade only now. You no need to convert into the what? Kelvin here now. Directly with centigrade you can complete. I say, I gave already formula. I naught at temperature T2 equal to I naught at a temperature of T1 into 2 power T2 minus T1 by 10 already I gave it. I gave this formula. By using this formula we can find I naught at what temperature we want? T2 is nothing but 90 degrees centigrade. 90 degrees centigrade only now. I naught is what at T1? I naught at T1 is given how much? I naught at T1 is nothing but 2 microamperes. 2 into 10 power minus 6 into 2 power T2 minus T1. T2 is nothing but the 90. T1 is nothing but the 10 divided by 10. Direct substitution in the problem only now. Understand now? Sir, can we do in other way? Yes, possible. 100% it is possible. Why not? This is one of the way only now. That means this problem only now. This problem can be done by one way, but one more formula is there now. That also we can use also. But that takes some time only now. Understand now? You can use any way. Allowed, 100% allowed now. There are different techniques also now. Just I gave, just by using the empirical formula, how we can find, just I am explaining that one now. Nothing more than that. Understand? Yes. This value is taken here now. But finally, that I naught is available. I naught is available 5.12 into 10 power minus 4. 10 power minus 4 amperes of current is possible. This is the required current at the given temperature only now. Understand now. Yes, I want to go to the next model now. Just one problem I want to explain by giving one formula only now. The next one, variation of next condition, variation of forward bias voltage, forward biased voltage, with respect to temperature. With respect to temperature, I can write with respect to temperature. Yes. But what is the meaning of this? You take a diode. In the diode, you got what now? Barrier potential we are having now. That barrier potential will be changing. Voltage across the what now? Diode will be changing with the change of the temperature also, he says now. When the temperature is increasing, width of the what now? Barrier will be reduced. And also what is possible, I said? Width is decreasing and also barrier potential also decreases only now. But that value is more important to do the next problem. That means the change of voltage with respect to the what now? Change of temperature. That voltage means voltage across the diode only now. Instead my point now, there is a barrier potential. That can be taken as a what now? Minus 2.1. This value will be minus 2.1. But generally, just like a formula, if you want to have means, I will give no problem otherwise. But exact formula, these are the values only I am giving you now. If you want to get the formula means, I can give now. They will apply V by T, voltage by temperature, minus eta into thermal voltage, into 1 by I naught, 1 by I naught, into d I naught by dt, d I naught by dt. By means of using this formula only now, dV by dt, change of this barrier potential with respect to temperature is calculated by this formula. But generally, nobody will apply this formula in the what now competitive exams only now. Directly one fixed value. For every 1 degree centigrade, what amount of the voltage is decrease will be given directly only now. That value directly you can use in the problems only now. I say dV by dt. I say dV by dt is taken as a what now? Minus 2.1 millivolts per degree centigrade. Per degree centigrade only now. For every 1 degree centigrade, 2.1 millivolts will be reducing. Reducing indicates that minus sign only. For every 1 degree centigrade rise in temperature, the decrease of the what now? The voltage across the diode is 2.1 millivolts only now. For 120 degree requirements, you have to multiply by 20, 2.1 into 20. This value is taken for germanium. For germanium, generally they will use this value. For silicon, in the competitive exam, it is taken as a what? Directly minus 2.3 millivolts per degree centigrade. For every 1 degree centigrade rise, minus 2.3 millivolts, it is going to decrease. For silicon, I can say. For silicon, we can use it only. That formula we can say. But generally, what now? Some books they will give now. One general value is there now. Even that value is taken, it is not a matter. 100% is allowed. Whether it is a germanium or silicon, no problem. No need to mark up these values. Generally, what they will take? The dV by dt is generally taken as a minus 2.5 millivolts per degree centigrade. Generally, they will put it only now. Otherwise, I will write clearly, you can understand. In general, very perfect means these are the values only now. In general, approximate value it can give. In general, it may be assumed, it may be taken otherwise. It may be taken a common value of value for germanium and silicon. Silicon, what value? That we can take dV by dt equal to, they will put generally minus 2.5 millivolts. Minus 2.5 millivolts per degree centigrade. In general, they will put minus 2.5 millivolts for any question only now. It's not a big matter. Doesn't have the light more change only now. Directly acceptable this value also. By using this formula, just I want to do one problem. Suppose anybody is appearing for any competitive exams, that will be useful now. Understand one problem if I have done, you can understand clearly now. In the foundation course, just the basics we are giving here now. Understand now. I want to give one problem based upon this. In given figure, silicon diode is carrying a constant current of 1 milliampere. What temperature when temperature 1 milliampere is possible. 1 milliampere. When temperature of diode is, this is a comma only, 1 milliampere. When temperature of diode is 20 degrees centigrade. 20 degree centigrade only now. VD is found to be 20 degrees now. Diode voltage is found to be 700 millivolts. It is found to be 700 millivolts. 700 millivolts. Understand now. 700 millivolts. Full stop. If in the problem what is asking you was, if temperature rises to 40 degrees centigrade. VD becomes dash. Diode voltage becomes approximately dash. One network also given here in the problem. This is connected with a current source 1 milliampere. This is a constant current. And here connected with one diode like this. Is asking to find this diode voltage across the diode. This voltage is asking to find at the given temperature. That is given problem. And also given options here. Option A is given here 40 millivolts. And option B is given here 660 millivolts. Option C is given here 680 millivolts. Option D is given 700 millivolts. Yes, these are the values are given. Anybody can try this question without my help, but I want to give some time. But I hope students can do easily this question without my help. Please try it in a given figure. Anybody can give which option is correct from the given problem? Anybody? Yes, I will do. Please watch. We want to find voltage across this diode. Voltage across diode is required. That is VD. How to find that VD value? I want voltage across the diode, VD value. Solution I want to take. Voltage across diode I want. In a problem, it is given clearly. When the temperature is maintained, but the current is constant only now, 1 milliampere. That constant 1 milliamperes, the current is passing. When temperature of the diode is at 20 degrees centigrade, that means a 1 milliampere, full stop you can put on, that is perfect way, you know. When temperature, because it is a constant current, it is given. When temperature of the diode is 20 degrees centigrade, diode voltage is found to be 700 millivolts. That's my point. Initially, diode is at the temperature of 20 degrees centigrade only. At the time, the voltage VD is nothing but this 700 millivolts. I can say this voltage is 700 millivolts only. 700 voltage it is having now. When the temperature is increasing, what happens? This 700 millivoltage is going to be still reducing only now. That means a decrease means what? In which material it is given here now? You please watch. This is silicon is given in the problem. In the silicon I gave already minus 2.3 millivolts per degree centigrade. It is going to decrease only now. Initially it is at a temperature of 20. Now the change of temperature, here the 40 we got. 40 means 20 degrees centigrade, it is increasing. 20 to 40 means difference is at 20 degree only now. For each 1 degree centigrade, how much? Minus of how much reducing? Minus of how much it is decreasing? 2.3 I gave it. 2.3 milli. This is a milli, this is also milli. 2.3 millivolts per degree centigrade. But the temperature for how much it is required? 20 degree. 20 becomes a 40. Difference is at 20. Into 20 I can multiply. Initially it is with 700 millivolts. Voltage across the diode. Due to increase of temperature now, change of diode voltage possible. How much it is possible? Minus y it is taken now. For every 1 degree centigrade, minus of 2.3 possible now, millivolts. For 20 millivolts, how much possible? Minus 2.3 into 20 only now. And finally, that voltage will be 654, it comes. That much millivolts it is possible. But in the options, which is it is possible now, approximately it is possible, 660 mostly possible only now. 660 millivolts we can put it now. That is approximately 660 millivolts possible. So which option is correct? You check it and do this one now. That way we can find out the what now? Voltage across the diode also. And next one more is possible. Next one more parameter is required. What parameter is required? Dynamic resistance. But I want to explain the dynamic resistance of the diode. Because sometimes you can expect the what now questions from the what now dynamic resistance also. I would like to explain what is that dynamic resistance. Dynamic resistance of diode only now. Dynamic resistance of diode, that is denoted by some symbol or suffix D only. That means when the diode is connected, that's my point. This point is very important. When diode is connected in the what now with AC supply. When diode is connected with the AC supply, at the time the resistance of the diode is to be taken as a what? Dynamic resistance only now. When we can use the name of dynamic resistance of the diode, when diode is connected with AC supply, its internal resistance can be denoted by symbol or suffix D. That is nothing but the dynamic resistance. We can say it only now. Understand now. That means in the where we are going to use this dynamic resistance, whenever the diode circuit is connected with what now? AC supply only now. AC supply it is given now. And sometimes they will connect AC and DC also. Mostly in the AC and DC, whenever it is connected, they are going to apply. Under AC analysis, they will apply this dynamic resistance. That's only one point now. Under AC analysis, the resistance of the diode is denoted by dynamic resistance only now. Thus, we can write one point now. It is also known as, it is also called as best. It is also called as AC internal resistance of diode. Internal resistance of diode. Internal resistance of diode only now. Internal resistance of diode. Internal resistance of diode only we can call. The concept of the dynamic resistance, the concept of dynamic resistance comes when diode with AC analysis. With AC analysis, whenever it is made, then they will use this dynamic resistance only. But how that AC resistance the diode is calculated? So we can write dynamic resistance is calculated by formula. Dynamic resistance RD can be calculated by what formula? RD is calculated by eta into Vt by I. Eta into Vt by I. They will use directly. When the diode is forward biased is given, you think it's so. This formula they will apply. When diode is forward biased, for forward biasing, this formula they will apply. For forward biasing, they will apply. But in case the diode is a reverse bias, sir, at the time, how I can take the what now? Dynamic resistance of the diode, sir. In that case, that formula will be taken as a what now? Eta into Vt by I naught. Only reverse saturation current is going to present. For reverse biasing, we can write down. For reverse biasing of the diode, this formula is applicable. When the diode is a forward bias, you can use this formula. Eta equal to, already I gave what now? Ideality factor. Vt is nothing but the thermal equivalent of the voltage. I is nothing but the capital I means diode current. I means diode current only now. I naught is nothing but the reverse saturation current only now. Now, I would like to give one problem in your hand. You try to tackle this. Yes, I will give one problem based upon this model. What is the value of RD? RD means dynamic resistance. For a PN junction, at T equal to 27 degrees centigrade. 27 degrees centigrade. I naught is given 1 microampere. I naught equal to 1 microampere. 1 microampere is given. And forward bias voltage is 0.2 volts and eta equal to 1 it is given. Suppose in a problem directly given, 1 only given. How we can determine this formula? How we can use this now? But in a problem what is given, you check it and start doing this question properly. Anybody can give answer for this question without my help? Any chance to give answer? What is the value of RD is asking? is asking to find RD equal to how much? At T equal to 27 degrees centigrade, 27 means it is a room temperature only now, in centigrade. In Kelvin means 300 Kelvin it comes only now, understand now. But anyhow, we know RD equal to what formula I gave it already? That formula directly I can write eta into Vt by, I gave already, I is given. Why this I? Because this is forward bias. If it is a reverse bias, I cannot take I. I must use the I naught only here. So eta value, but I is unknown. I is nothing but here ID only now. I equal to ID, diode current only. I or ID, it is acceptable. Where ID equal to, we know very well, I naught into what? E power voltage across the diode by eta into Vt. V or V naught, same only now, minus 1. Directly I am writing now. Even you neglected one, no problem. Otherwise, even you apply directly this formula, no problem here now. I naught is given or not given in the problem? You check it here now. And I naught equal to 1 microampere is given. 1 into 10 power minus 6. E power voltage across the diode is given 0.2 voltage. 0.2 voltage here given. Divided by eta value is nothing but 1. Vt is not given, room temperature. Room temperature means we know what its value, 26 millivolts. I can write directly. 26 milli minus 1 I can use. Use calculator, you will get the diode current directly here now. The diode current comes as approximately, it comes as 2.19 milliampere. 2.19 milliamperes, mostly it is possible. Once you got the value of diode current, you can measure RD directly. RD equal to how much? Eta is a 1. Vt is nothing but how much here? The Vt is nothing but 26 milli, we know. Divided by diode current, we got approximately 2.19 into 10 power minus 3. If you are using the calculator, its value comes as 11.87. Its value will be 11.87 possible. 11.87 ohms possible. That much value possible. That is the resistance of the what now? It's dynamic resistance of the diode is possible. That is the way we can do it. Understand my point now? If the students are willing to do means I will give one problem. You make an effort. If you are getting answer, very good. Understand now? I will give one question now. Understand now? You make an effort. Just for practice, I want to give in your hand this question now. Understand now? I want to give the problem like this now. You please try this question as a homework. For a given semiconductor, if I naught equal to 30 microamperes, 30 microamperes, eta equal to 1, T equal to 125 degrees centigrade, not given here room temperature. T equal to 125 degrees centigrade is given. When the temperature changes, thermal equivalent of voltage Vt value also changes. So you must find for the temperature Vt value. Don't put 26 millivolts. 26 is only for millivolts for where? At room temperature only. It's not a room temperature here now. Understand? What is asking? Calculate value of RD for 0.2 volts in forward bias. In forward bias I want. In forward bias. That is the given problem. But one condition I wish to give in your hand only now if you want here now. But you try this question as a homework. But here you know very well, I didn't give the formula for the what now. When the temperature changes, how to find the thermal equivalent of the voltage. I will give understanding purpose here now. Thermal equivalent of the voltage can be calculated by T by temperature T by 11,600. They will apply. By using this formula directly, thermal equivalent of the voltage you can find. The T value what now? It must be in Kelvin. It must be in Kelvin only now. But 125 centigrade you convert into what now? Kelvin. The T by 11,000 you put it now. That means around 398 possible. 123, 125 plus 273. Add up you will get now totally. There is a T divided by 11,600. Thermal equivalent of the voltage we will get now. Okay, anyhow, you try this question. If you are getting, very good only now. Thank you. Next class we can start the BJT. These are the basics of the what now? PN junction diode only. Okay, then we can close.